Hello, Namaskar and very good afternoon to all the viewers connected with us on NCERT's live and interactive program. I am Anu Gupta, your host for this session. Dear viewers, आप हमसे जुड़ गए हैं PME विद्या के चैनल नंबर 12 से. And for this 1 hour, we have brought to you a session for class 12 students for the subject physics. और आज का हमारा टॉपिक रहेगा current electricity. Apart from this channel, we are also streaming live on our YouTube channel which goes by the name NCERT Official. You can become a part of our live interaction by sending in your queries, questions and feedback in the live chat box of our YouTube channel. Also dear viewers, if you wish to get connected with us on this topic, do reach out to us telephonically also, and here are our numbers 8800440559, which is flashing right now on the screen. Also, if you wish to write to us in detail, please note down our email address which is class specific, and it is dth.class12@ciet.nic.in. तो आइए दर्शकों, हम बात करते हैं अपने टॉपिक के बारे में, करंट एंड इलेक्ट्रिसिटी. करंट इलेक्ट्रिसिटी बहुत ही इंटरेस्टिंग टॉपिक है और हमारी रियल लाइफ से जुड़ा हुआ है. चाहे एक बल्ब को पावर मिलने की बात हो या आपके मोबाइल फ़ोन के चार्जिंग की बात हो, सब कुछ ही एवरीथिंग इज़ पावर्ड बाय करंट इलेक्ट्रिसिटी. और हमारे इस टॉपिक को डिटेल में बताने के लिए हमसे जो एक्सपर्ट जुड़े हैं हमारे स्टूडियो में, आइए हम उनसे भी मिलते हैं. सो हमारे आज के एक्सपर्ट जो हमारे साथ जुड़े हैं उनका नाम है मिस्टर ईश कुमार गोगिया. सर इज़ फॉर्मरली PGT फिजिक्स फ्रॉम केंद्रीय विद्यालय संगठन. सर बहुत बहुत स्वागत है आपका इस सेशन में.
नमस्कार, थैंक यू.
जी, I also like to welcome our Indian Sign Language experts who are translating the entire session for you in sign language with us. We are joined by Miss Ambu Sakshi and Miss Nena. You are currently watching Miss Ambu Sakshi on the screen. Namaskar and very welcome to the session to both the interpreters. So अब बिना देरी किए मैं दर्शकों को ले जाना चाहूँगी अपने एक्सपर्ट के पास और जानेंगे कि आज हम क्या क्या पढ़ने वाले हैं इस सत्र में. सर.
Thank you. Let's begin. Dear learners, in this unit on current electricity, today we will be talking about the electric current. Means we will learn what is the meaning of electric current, the types of current, SI unit of current, the unit in which the current is measured, and we will also talk about the reason why current is taken as a scalar quantity. In electrostatics, we consider all charges to be at rest. This is what you have learned in the earlier unit in class 12 physics. The charges in motion constitute electric current. You all know from your knowledge of charges in previous classes that electric charge is of two types, positive and negative. The electrons, which are mobile particles and very light particles of fixed mass, they are negatively charged. You already know about it. In nature, we have an example of the current. Lightning is a natural phenomena in which charges flow from the clouds to earth through atmosphere. However, sometimes the effect is disastrous. This is not the current which we are looking for and we want. Such flow of charges in lightning is never steady because off and on we get lightning and hence the charge flow. However, on earth, in devices like torch and cell driven clocks and other devices which we use in daily household, the current is steady and is providing useful service to mankind in various fields. Why electricity or electric energy is important, we can understand this by one simple advantage, that current, the electricity or electric energy can easily be converted into other forms of energy. Mechanical energy in fan heat energy in heater and geyser, light energy in LEDs, fluorescent tube lights, and so on. So this is one form of energy which is most widely used because it is most conveniently converted to other forms of energy. Even sound, yes, you know, in the TV radio sets we convert electric energy into sound energy. Hence electric energy is most suitable, most convenient form of energy for us to perform various functions. Now, what is electric current? The electric current term is the rate of flow of charge with time through any cross section of a conductor. If a charge Q is transferred through a conductor in a time t, then mathematically we take current as total charge divided by total time, or Q by T, where Q is symbolically denoting the total charge and T is the time in which this charge is transferred through the conductor. The expression Q by T, or total charge by total time, gives value of average current. You can correlate with the average speed. Average speed is total distance over total time. Similarly, average current is total charge over total time. It gives us rate of flow of charge when the current is steady. Otherwise, it is average value of the electric current. Now, if the current continues to change with time, then we will obviously not be able to give it a fixed value. In such cases, we express the instantaneous value of current, that is value of current at a particular given instant of time. And this we know mathematically is differential, the rate of change of charge, rate of transfer of charge with time. dt here denotes infinitesimally small time, and dq is the charge transferred in that infinitesimal small time. So if you want to find the total charge transferred in t second, then mathematically you have to integrate current with respect to time. You have the relation on your screen, q is equal to integral I dt within time limits 0 to t seconds. Now, coming to types of current, there are two different ways of classifying current. One is steady current and varying current. Other classification we'll study a little later. Steady current, it is the current which does not change with time. Now, we'll show this, study this current with the help of a graph. See this, look at curve 1. Curve 1 is parallel to the time axis. It is because the value of current does not change with time. So, for steady current, I versus t graph is a straight line parallel to the time axis. You can see other graphs 2, 3 and 4. Here the value is changing with time. It's not steady, it is changing with time. 5, this is yet another graph, I versus t graph, where value is changing with time. Now, other type of current is varying current. As the name suggests, the value of current will change with time. Here in the upper diagram, 2 and 3 are the curves which represent varying current. In fact, except one, all other 4 graphs, 2, 3, 4 and 5 represent varying current, because from the graph you can see that the value of current is changing with time. Now, another classification of current is in the form of direct current and alternating current. First, the direct current. It is the current which continuously flows in same direction. That is, the value of this current will continue to be either positive or negative all the time. Sign will not change, direction will not change. In the graphs, 5 graphs which we have on the screen, 1, 2, 3 and 5. These are the graphs which represent direct current because their value is always positive, never negative. You can see curves 1, 2, 3, 5, all these represent direct current. The direct current need not be steady. The only condition is the direction should not change. Value may change. 1 is steady direct current, 2, 3 and 5 are varying direct currents, 4 is not direct current. Now the other type of current is alternating current. It is a current which reverses direction of flow after regular intervals of time. This you can see in curve 4. In curve 4, for some period of time the current is positive. You can see the upper two halves above the time axis, the current is positive, means it is flowing in a particular direction.
Ji.
Then we have lower halves also in this curve,
Ji.
where the current is negative. And one thing more I will like to add here, the household supply is always alternating current, or in short we call it AC.
But why is this so, sir? I would like to ask as a viewer also कि हमारे घर में AC ही करंट हमेशा क्यों आता है?
There is a reason for the supply of alternating current. Although the detailed study will follow in a different lesson, alternating current later in your syllabus.
Ji.
But here, since you have asked this question, I will love to answer this question.
Ji.
Partly, alternating current or AC, which reverses direction after regular intervals of time, is very useful and it has certain advantages over the direct current. You must be knowing that the supply in households is 220 volts
Ji.
AC. If we want, or if we have a device which operates on a lower voltage or higher voltage, we can very easily convert this voltage from 220 to above 220 or below 220. For example, you have seen the mobile chargers,
Ji.
the very small piece,
Yes.
which is a block always available around us. It converts 220 volts AC to about 5 volts DC. If you look carefully on your and read the fine prints on the mobile charger,
Ji.
you will see that the output it provides is about 5 volts,
Right.
and that is direct current. So that
Ji.
small device is changing AC 220 volt available voltage to about 5
5
volt,
DC. Ji.
and it
Right.
is also converting it to direct current, which is required for charging. So wherever we have to convert voltage, increase or decrease, we technically say step up or step down voltage, the AC is a better choice,
Right.
and we can conveniently convert it into DC as and when we require.
Ji.
Now current is a scalar, that is, it has only magnitude and no direction. Interestingly, we assign a direction with current to the current, as we will see just now, but still it's a scalar. This dilemma we will solve with the help of an example, and we compare it with vectors, which will clarify why the current is taken as a scalar quantity. The SI unit of current is ampere. Since current is defined as the ratio of charge to time, 1 ampere is the current through a conductor if 1 coulomb charge passes through any section of a conductor in 1 second. I like to add here that this is not an internationally accepted definition of current.
Right.
The actual internationally accepted definition of current is in terms of the magnetic effect, which you will study in the next unit, magnetism and magnetic effect of current.
Ji.
But here basically we define coulomb in terms of ampere. But here, because we had the relation I is equal to Q by T, we are taking 1 ampere to be the current if 1 coulomb charge passes through a section of a conductor in 1 second. Smaller units of current are milliampere, which is 1,000th of an ampere, 10 to the power minus 3 ampere. Symbolically, we write it as 1 small m capital A, milliampere. Still smaller unit is microampere, 1 mu A symbol, and it is 1 millionth of an ampere, 10 to the power minus 6 ampere. Now, conventional direction of current. We know that current is rate of flow of charge. The charge being transferred may be positive or negative. By convention, the direction of current is taken to be same as that of motion of the positive charge.
जी.
If positive charge moves from left to right, the current is also taken to flow from left to right. You can see this diagram. In this diagram, the red dots represent positive charges. They are moving, the positive charges are moving from left to right. Therefore, conventional direction of current I, the symbol of current is I, is also from left to right. For flow of positive charges from left to right, the potential V1 should be higher than potential V2. So here I repeat, direction of current is same as the direction of motion of the positive charge. Electrons carry negative charge. Therefore, the electrons move in a direction opposite to the conventional direction of current. See this diagram. In this diagram, the black dots represent electrons carrying negative charge. The electrons are moving from left to right, that is, negative charge is flowing from left to right. This effectively means that positive charge is moving in opposite direction. Therefore, current is opposite to the direction of motion of the or flow of the electrons. You can see in this lower diagram, electrons are moving towards right and current I indicated by red arrow is pointing towards left. So remember, the direction of drift of electrons is opposite to that of the conventional direction of current. Now, after assigning the direction, we are now making a statement that current is a scalar quantity, means it doesn't have, we should not call it a vector quantity. Now, why so? For this, we need to compare the current with the vectors. Here we have a block in the diagram, and on this block two forces F1 and F2 are acting at an angle theta between them. These two forces F1 and F2 acting together on the block will give us a net effect or net effective force F. The value of the effective force, which we also call resultant force, is given by the triangle law or parallelogram law of vector addition that we have studied in grade 11, and the relation is F equal to square root of F1 square plus F2 square plus 2 F1 F2 cosine theta. The value of the resultant force will change if the direction of F1 or F2 or both is altered. So, force is a vector quantity because any change in direction of force alters its effect on the block. Therefore, force is a vector. The forces can be added by laws of vector addition. In contrast, let's now talk about current and see why current is a scalar quantity. See the upper line, it represents a wire carrying current in the direction of arrow, that is left to right. Suppose this wire is part of a circuit wherein we are using this wire to light a table lamp Okay. If you bend this wire as shown in the lower part of this figure, it does not affect the light emitted by the electric lamp. So, the direction does not matter here. Had it been a force, the effect would have changed. But here bending the wire means the current slightly deviates from the straight path, but its effect remains the same. Therefore, current is a scalar quantity. You have the statement on the screen. Bend in the wire carrying current does not alter effect of current on the electric lamp or the fan or the device which is used to operate. Another diagram you have here, we have two wires. The left top wire carries a current of 2 ampere, the lower one carries a current of 4 ampere, and the two wires are at an angle theta. The two currents add up to give us 6 ampere current. So, if the wires carrying 2 ampere current or 4 ampere current, they are bent, turned, the value of total current will not alter, it will still remain 6 ampere. That is, current obeys the scalar addition relations. So, unlike vectors, current follows laws of scalar addition. Therefore, it is a scalar quantity, and you can compare it with forces. If the direction of F1 or F2 shown in the previous diagram, if changes, the effect on the block changes, which is not the case for current. Therefore, current is a scalar. The conventional direction which we have assigned just gives the direction in which the positive charge is being transferred in the device. Now, having studied the 4 or 5 small types of current, let us now further proceed in the lesson. Now, we will study the current flow through a conductor. That is, we will talk about the mechanism of flow of current, how and what makes the current flow through a conductor. We will talk about a new term, the drift speed. We will introduce and discuss its meaning. There is yet another term, relaxation time, about which we will talk in this lesson. Then we will obtain a relation between current and drift speed. Remember, drift speed of electrons is responsible for flow of current, as we will discuss a little later. And then we will also define a term, current density, and see its significance and unit. Now, mechanism of current flow in the conductors. The conductors have free charge carriers, typically free electrons. The electrons are never at rest, they are in constant random thermal motion. Thermal motion means motion due to their heat energy. See, in this conductor AB, the electrons are moving in a zigzag fashion. XY is a cross section of the conductor. The random motion, although it is at in this random motion or thermal velocity of electrons is fairly high, about a few kilometers per second, but this random motion does not result in flow of electric current. Reason, we will see why the random motion does not result in flow of current. In the diagram, you can see, if you look at the section XY carefully, the number of electrons crossing XY from left to right is equal to the number of electrons crossing from right to left. That is, there is no net transfer of electrons across XY. Since no electrons are transferred, no charge will be transferred, and since no charge is transferred, current, that is the ratio of charge to time, will be 0, because charge transferred is 0. You can see here the reason once again, number of electrons across XY from left equals the number of electrons across xy from right. No net transfer of electrons, no net flow of charge, no current. Now, since the motion of electrons, velocities of electrons, free electrons is zigzag, random, the average random velocity of electrons of the conductor is 0. Here, if u1, u2, u3, u4 and so on represent the random thermal velocities of the electrons in the conductor, the average velocity happens to be 0. But here remember, we have not applied any external electric field. It is pure thermal motion, not affected by any other external factor. So, in absence of any electric field, the average velocity of free electrons is 0. Therefore, the current is 0. Now, let us apply a potential difference across the ends of the conductor, and A of the conductor shown is at a potential V1 and B is at a potential V2, and we have V1 greater than V2. The potential difference between the ends A and B develops an electric field from A to B. From your knowledge of electric field in the unit of electrostatics, you know that the electric field acts in the direction of decreasing potential. Since the potential decreases as we move from V1 to V2 or left to right, the electric field in this diagram or on this conductor or within this conductor is from left to right, the direction of decreasing potential. The direction of electric field by convention is the direction of force on positive charge. Since the electrons carry negative charge, the electrons experience a force against the direction of the electric field. Field from left to right, force on free electrons from right to left, opposite to the applied field. Now, since there is a force experienced by the electrons from right to left or against the direction of the field, the number of electrons crossing xy from right to left exceeds the number crossing xy from left to right. This you can see in the diagram. Greater or larger number of electrons are drifting past xy from right as compared to the free electrons drifting past xy from left to right. This is also indicated in the diagram by means of the arrows. You can see the arrow, the lower arrow represents the number of electrons from right to left. The longer arrow, the upper arrow represents the number of electrons from left to right. Since the number is smaller, we have used a smaller arrow. So there is a net transfer of free electrons across a section of the conductor from right to left. This causes a flow of current through the conductor. The current flows in the direction of decreasing potential, higher potential to lower potential. The current is flowing from left to right, but there is a net transfer of electrons from right to left. This is in presence of electric field. So, when an electric field is present, each electron experiences a force opposite to the direction of the applied field, and therefore the force causes acceleration in the electrons. We will have the expression for acceleration. Acceleration is given by force over mass. Here in this equation, A is the acceleration, minus E is the charge on the electron. So, charge here we have minus E, electric field is capital E, m is mass, therefore acceleration is force upon mass, that minus E into capital E over m. under the action of electric field, free electrons gain a velocity component in addition to their random thermal velocity. Look at this diagram very carefully. This diagram, if you, let's now to begin with concentrate on the blue bold lines in the diagram. The blue bold lines here represent the path followed by an electron, a free electron, as it moves from A to B. See the initial point A and the final point B. The electron moves along various straight paths, finally ending up at the point B. So here between if you take any straight path starting from A, let's look at the first straight path. Here the electron is free to move, not under the effect of any force, because the blue lines represent absence of electric field. So here the electron is moving along a straight path, no force, no change in direction, no acceleration. Again, at a particular point it bends, there is a sudden turn in path. This is because the electron has collided with an atom. When it collides with an atom, momentarily it changes direction. Similarly, other bends in the path, they show the collision point of the free electron with the atom. Now coming to the dotted black lines, here the effect of electric field comes into picture. We have applied electric field. In the diagram the field is shown to act towards left. So the force on the electrons, and hence the there will be a slight shift in the electron path towards right. There is an acceleration to force towards right, acceleration towards right, therefore the path of the electrons will change. But it is free between the two collision, the electron is free to move it without the effect of any atom in the crystal lattice. You can see here, during motion free electrons collide with positive ions of the metallic lattice and lose additional kinetic energy. So between two collisions, when the field is acting, force will act, the acceleration will be there, electron will be speeded up opposite to the direction of the applied field. It will gain energy but lose it in subsequent collision. The gain in energy or velocity lasts for a short time until the next collision. This is very important and must be kept in mind, that when you apply electric field between two collision, force is acting, acceleration takes place, velocity increases, kinetic energy increases, but this increased kinetic energy is lost in subsequent collision. Let's say the electron is free for time tau 1, tau 2, tau 3 and so on, that is the time elapsed between two collisions. Then we take the average of the mean free times. The average free time elapsed between two successive collisions of an electron is called mean free time or relaxation time. The symbol used for it is tau, and mathematically the mean free time is calculated as average of the various free times of the electrons, that is tau is equal to tau 1 plus tau 2 plus tau 3 and so on, divided by the number of the time intervals taken. This is mean free time. In this average time, free electrons gain average velocity given by Vd equal to 0 plus a tau. Now here we are using the relation V is equal to U plus AT, which you have been learning since class 9. The initial average velocity of the electrons, by initial average velocity of electrons we mean the velocity in absence of electric field, that is 0. Therefore U is 0 and we have acceleration expression and the average time. the expression for the drift speed is minus small e, the electron charge, into capital E, the electric field, divided by m, the mass of the electron, multiplied by the average free time or relaxation time tau. Under given conditions, the drift speed does not change with time. Why the drift speed does not change with time in spite of the acceleration? Here the reason is that whatever kinetic energy or speed electron gains, it loses in the subsequent collision. This average velocity Vd is called drift velocity of the free electrons. It is related by the formula in the which you have on your screen. We have a negative sign which indicates that the drift speed or drift velocity is directed opposite to the direction of the applied electric field. For the purpose of definition, drift velocity is the velocity with which free electrons drift towards positive terminal of a battery under the effect of external applied electric field. That is from lower potential towards the higher potential.
जी.
Now we will obtain an expression for electric current. For the purpose we are taking this conductor. Let's see what are the parameters which we will be using. We have a conductor with uniform area of cross section A. The cross section is shown in the diagram. The conductor has n free electrons per unit volume, and the current through the conductor is denoted by capital I. You can see two sections X and Y in the conductor. We will talk about these. Let Vd denote the drift speed of free electrons in the conductor. We know we have the current is flowing, therefore the electrons are drifting with a speed Vd, which we call the drift speed of free electrons. Here we have two sections X and Y of the conductor separated by a distance numerically equal to Vd. Here Vd is a symbol used for two things. It is the magnitude of the drift speed and also the distance between the sections X and Y. Numerically these are equal. Now in this diagram, let's concentrate on the region between X and Y, that is the region of length Vd numerically equal to the drift speed. Any electron to the left of X, you have an electron in the diagram, it will cover a distance Vd in 1 second. The time we are taking is 1 second. It will cover a distance Vd towards right, and it has reached a point just to the left of Y. That is, this electron has not crossed Y in 1 second. However, electrons between X and Y, they will cover a distance Vd in 1 second and they will drift past Y in 1 second. We simply put all electrons within X and Y, they will be able to cross Y in 1 second because the distance is Vd, which is the distance covered by electrons in 1 second. This is very important. All free electrons between X and Y over a length Vd and area of cross section A cross Y section in 1 second. So this is again I am reading it for you. In 1 second, all free electrons between X and Y cover a distance Vd and hence drift past Y. Now current is charge per second. So whatever is the charge crossing Y in 1 second, that will give us current. Now charge crossing in Y in 1 second is the charge on free electrons which are present between X and Y. So here charge per second is number of free electrons between X and Y multiplied by E, because this is the number which is crossing Y in 1 second. Now number of electrons is given by small n, number per unit volume multiplied by volume between points or sections x and y. The volume is given by area into distance. Area is A and the length between x and y or distance between x and y is Vd. Therefore, the volume between x and y is AVd. Therefore, the charge transferred in 1 second is small n, the number of free electrons per unit volume, capital A, the area, Vd, the drift speed, and E, the electron charge. This is charge transferred in 1 second, and by definition, this is the current. Therefore, current I is NEAVD. This is the expression for the electric current. Now, current density is a new term which we define as current per unit area of cross section of the conductor. We will get an expression from it from the previous relation I is equal to NEAVD. You can see here the current density symbolically denoted by capital J. It is I over A, the current over area, or J vector, the current density vector is minus NEAVD over A. Area is common in numerator and denominator, so the current density is minus NEVD. Vd is the drift velocity vector. The negative sign again indicates that the direction of current density vector is opposite to the drift velocity. Since the current density is current per unit area, the unit will be unit of current ampere divided by unit of area meter square, that is ampere per meter square or ampere meter minus 2. As said earlier, the negative sign implies that electrons drift opposite to the conventional direction of current. Therefore, we can write current I is as J dot E. So, current is the scalar product of current density vector and the area vector. Now, based on the relation that we have studied, here is a numerical example. We have two conducting wires X and Y of same diameter but different materials joined in series across a battery. Please note the parameters very carefully. You have two conducting wires X and Y. Diameter is same. Remember, they have same diameter. They are made up of different materials. They are joined in series across a battery. Series means end-to-end connection. So whatever is current flowing through X will also pass through Y. The number density of free electrons in the two conductors are different, as is given in the statement. Number density of free electrons in Y is twice that in X. We have to find the ratio of drift velocity of the electrons in the conductors X and Y. Let's proceed with the solution. For wires joined in series, current is equal, that is Ix, the current through X is equal to current through Y. Using the relation for current NEAVD, we can write Ix equal to Iy can be replaced as Nx, the number of free electrons in X, multiplied by E, the electron charge, into area into Vx equal to Ny Ea Vy. Now Ny is given to be twice of Nx. So you can write NEAVD equal to 2N Ea Vy. Ea is common on the both sides. So therefore you get Vy by Vx is equal to 1 over 2, which is the desired ratio of the drift speeds of the electrons in the wire Y to that in the wire X. Another example, estimate the average speed, drift speed of conduction electrons in a copper wire of cross-section area 1 into 10 raised power minus 7 meter square, carrying a current of 1.5 ampere. the number density of conduction electrons is given to be 9 into 10 to the power 28 per meter cube. The data is recorded given area, current and the number density of electrons is on the screen. We use the expression I is equal to NEAVD to calculate the drift speed. The drift speed will be given by I over NEA. Substituting the various values, you can calculate the drift speed, which by calculation comes out to be 1 millimeter per second. So this is a small drift speed with which the electrons move against the drift. I should not say move, drift against the direction of the electric field.
But sir, जैसे कि आप बता रहे हैं, this is a very small speed, I should say.
Yeah.
If we observe in our households, as soon as we switch on the switch, as soon as we plug it,
Yes.
the electricity is there in the bulb. तो अगर इतनी slow speed है electrons की, how is it possible with this speed?
You asked a very good question, and this is a question which obviously should come in your mind. Say, I mean, we know that when we switch on any circuit, the wire may be 10 meter, 20 meter, the current flow is instantaneous.
Right.
The electric lamp is instantaneously on, the fan instantaneously starts rotating.
Right.
Despite this very small 1 millimeter per second velocity of the electron. I'll like to reword your
Sure.
question here. You can see electron drift speed is estimated to be only a few millimeter per second. How then is the current established almost instantaneously in a circuit? This is how
Absolutely.
we can
Yes.
put the question you have asked. Here the answer is when the switch in an electric circuit is turned on, the electric field is established throughout the circuit almost instantaneously with the speed of light, setting a local electron drift. Now what is this local electron drift? Remember, we don't have to start an electron from negative and travel all through the length of the wire and reach the positive terminal.
जी.
The 2 points are always connected with the help of a conductor. Free electrons are present everywhere.
जी.
When we switch on the current, we are in fact giving a command to the electrons through electric field to start drifting from negative towards positive against the direction of the electric field. So they suddenly start moving from their original position. Every electron moves towards higher potential. Therefore, the current flow is instantaneous.
Right, okay.
And then when you switch it off, there is a command that electric field is over, stop the electrons, stop drifting
जी.
in either direction.
Right.
So that
Okay.
is how the
That's wonderful.
yeah. So establishing a current does not mean that electrons shift from one end of the conductor all the way to the other end. That is why the current flow is instantaneous. The electric field just starts a drift of the electrons under the action of the electric field, which is an instantaneous process.
जी.
Let's now discuss Ohm's law,
जी.
linear devices, resistance and resistivity. We will also obtain expression for resistance and resistivity time permitting.
जी.
Ohm's law, this law gives a relation between potential difference and current for conductor. It states that for a conductor under fixed temperature, stress etc., potential difference across the terminals of the conductor is directly proportional to the current passing through the conductor. Mathematically we say V is proportional to I or V equal to I into R, because proportionality has been changed to an equation we always have to introduce a constant. That constant inserted here is capital R. We call it electric resistance of the conductor.
Right.
The relation V proportional to I or V equal to IR implies that V versus I graph will be linear or a straight line, as you can see here. The resistance is the property of a conductor by which it opposes the flow of current passing through itself. The resistance is also a scalar quantity. The resistance of a conductor varies with its shape,
जी.
size and nature of the
Material.
The SI unit of electric resistance is ohm, and resistance is V over I. The symbolically we denote this unit by a Greek symbol omega on the screen.
जी.
1 ohm is 1 volt over 1 ampere because R is V over I. We can define 1 ohm as the resistance of a conductor which allows 1 ampere current through itself when a potential difference of 1 volt is applied across its terminals or ends. Now there are two types of devices, ohmic and non-ohmic devices. An ohmic device is the one which obeys Ohm's law. It is also called a linear device because the VI graph for such a device is a straight line. Example is a metallic conductor. Now coming to non-ohmic or non-linear device. A device is non-ohmic or non-linear if it does not obey Ohm's law. The graph for non-ohmic device, VI graph, is a curve. Here you can see, look at the right side of y-axis. The graph is a curve. Here we are applying voltage in forward direction. The current is in forward direction. And if you reverse, the graph is not similar. Had it been a conductor, the graph on positive side means when you apply the potential difference from left to right or right to left, the behavior is similar. But for this particular special device, diode, the very character, the very behavior, the value of current for the same potential in one direction is not as it is in opposite direction.
Right.
Therefore, it's a non-linear device. It is diode. You will study about the diode in detail in a later lesson.
Right. All right. So, I am guessing this is the end of the session, dear viewers.
We'll be talking about Ohm's law in detail in the
upcoming
next lesson.
Right. Of course, yes. So, अब जब हम अंत पर आ गए हैं सेशन के, हमारे साथ जुड़े थे ईश कुमार गोगिया जी, तो मैं सर को बहुत बहुत धन्यवाद देना चाहूँगी. सर, बहुत बहुत धन्यवाद हमें इतना इन्फॉर्मेटिवली इस टॉपिक के बारे में बताने के लिए. थैंक यू सो मच. और डियर दर्शकों, मैं अब आपको एक बार फिर से बताना चाहूँगी कि हम जुड़े थे 2 से 3 बजे एक बायोलॉजी के लेसन के लिए, जिसका टॉपिक था द लिविंग वर्ल्ड एंड बायोलॉजिकल क्लासिफिकेशन. साथ ही 3 से 4 बजे हम जुड़े हैं आपके लिए करंट एंड इलेक्ट्रिसिटी टॉपिक के साथ, जो कि फिजिक्स का कक्षा 12वीं का एक टॉपिक है. जो भी आपके डाउट्स, क्वेरीज हैं, ज़रूर हम तक पहुंचाएं लाइव चैट बॉक्स के थ्रू या फिर ईमेल के थ्रू. सर हमारे लिए बहुत ही डिटेल्ड लेकर आए थे एक्सप्लेनेशन ऑफ दिस टॉपिक, बी इट थ्योरी, बी इट प्रैक्टिकल फॉर्म, बी इट न्यूमेरिकल फॉर्म. सो आई एम गेसिंग एंड आई एम श्योर हमारे व्यूअर्स, हमारे बच्चों को बहुत ही ज़्यादा इससे अंडरस्टैंडिंग क्रिएट हुई होगी. Now we come to the end of this session and keep learning, keep growing. I am Anugupta, your host for this session, taking your leave. Namaskar.